I want you to imagine for just a second that you are 13,000 feet underwater.
Oh, wow. Okay.
Yeah, right. You are completely enveloped in pitch black darkness. It is freezing cold. The pressure is just unimaginable. And, well, according to absolutely everything we know about biology, the oxygen levels down there should be slowly but surely depleting.
Right, because as whatever marine life is down there breathes in this isolated, lightless environment, the oxygen gets used up.
Exactly, it gets used up. But scientists recently sent equipment into that exact abyss and found basically the exact opposite.
Which is wild.
Right. Oxygen levels weren't dropping, they were mysteriously surging. Like, in some cases, they were exceeding the oxygen levels you would find at the sunlit surface of the ocean.
I mean, it completely shatters a paradigm we've relied on for over a century. You know, we're all taught from grade school that oxygen comes from sunlight.
From photosynthesis, yeah.
Exactly. Plants, algae, phytoplankton, they all use the sun's energy to create the oxygen we breathe. So to find oxygen spontaneously generating in the darkest depths of the ocean, where sunlight has literally never penetrated, it makes you stop dead in your tracks.
It really does.
It forces you to rethink the foundational rules of chemistry and biology.
And that is the mission of today's deep dive. We are exploring the scientific mystery of what researchers are now calling dark oxygen. We are going to break down how these deep-sea stones that basically look like, I don't know, lumps of coal or small potatoes are acting as literal underwater batteries.
Which is still hard to wrap my head around.
I know. And we're also diving into this trillion-dollar environmental tug-of-war over deep-sea mining that this whole discovery has triggered.
Because the stakes here, they extend far beyond just some quirky oceanographic anomaly. This challenges our fundamental understanding of how oxygen is made. It forces us to reevaluate how life on Earth might have evolved in the first place.
And what it means for the oceans right now.
Right, it has massive immediate implications for the future of our oceans. And as we'll explore toward the end, it completely changes the criteria for how we might look for life on other planets.
So, okay, let's go back to 2013, to the middle of the Pacific Ocean. A deep-sea scientist named Andrew Sweetman is leading this expedition to the Clarion-Clipperton Zone.
Often called the CCZ.
Right, the CCZ. It's this massive, relatively unexplored stretch of ocean floor between Hawaii and Mexico. And Sweetman sends these automated seafloor landers, specifically devices called benthic chambers, about 5,000 meters down.
Just for context, a benthic chamber is essentially this specialized titanium cylinder. It drops to the ocean floor, drives itself right into the mud, and seals off a pocket of deep water along with whatever seafloor life is trapped inside of it.
So it creates this little isolated bubble.
Yeah, exactly. And then it uses sensors to monitor the chemical changes in that bubble over several days.
So Sweetman fully expected to measure the respiration rate of the seafloor. Like, he expected the oxygen to slowly tick down to zero, but instead the sensors showed this massive, steady increase in oxygen.
Which, I mean, as any scientist will tell you, immediately looks like an equipment failure.
Oh, absolutely.
When your data violently contradicts the laws of physics and biology as you understand them, your very first assumption is, well, we have a faulty sensor.
Yeah, they didn't believe it at all. They hauled the landers up, they recalibrated all the sensors, they even tested entirely different equipment on different expeditions over the next few years, and they kept getting the exact same result. The oxygen was increasing.
It's just wild.
Okay, let's unpack this for a second, because finding oxygen spontaneously generating in a lightless, crushing deep-sea environment is like, it's like walking into a sealed, pitch-black cave and finding a thriving, sun-loving jungle growing inside. It just shouldn't be possible.
It shouldn't. And that impossibility drove Sweetman to look closer at the physical environment itself. Like, the seafloor at the CCZ isn't just mud. It is famously littered with these small, dark, potato-shaped stones called polymetallic nodules.
Potato batteries.
The potato batteries, exactly. And these nodules, they take millions of years to form. They're layering metals and minerals from the seawater incredibly slowly, almost like a pearl forming inside an oyster, but, over geological timescales.
Right.
So Sweetman hypothesized that these rocks might be the missing variable. So he partnered with a chemist, Dr. Franz Geiger, to run some tests in a controlled lab.
And they hauled these nodules up from the seafloor, and honestly, their methodology to prove this wasn't just some undiscovered deep-sea bacteria making the oxygen is brilliant.
It really is.
They took the nodules and completely sterilized them using mercury chloride, which is a highly toxic compound that basically guarantees any oxygen-producing microbes on the surface of the rocks are unequivocally dead.
Dead as a doornail.
Exactly. Then they place these sterilized nodules in an airtight jar filled with cold, salty water, perfectly mimicking the temperature and the salinity of the deep sea.
And the oxygen levels in the jar didn't just stay stable, they tripled.
Wow.
Tripled.
Yeah. The source of the oxygen was abiotic. It was a chemical reaction completely independent of biological life.
Okay, I have to push back on the mechanics here just a bit, because this is where a lifeless rock, seemingly breathing out oxygen, just defies logic for me. How exactly does a rock generate gas?
Well, it doesn't generate gas directly. It conducts electricity, which then alters the water.
Okay.
Think of the chemistry of a standard AA battery you'd buy at the store. A battery requires three things, right? A positive terminal, a negative terminal, and an electrolyte fluid between them that allows an electrical charge to flow.
Sure, basic chemistry.
Right. Well, these polymetallic nodules naturally contain high concentrations of manganese. And manganese is a transition metal that is widely used to create the positive terminal in a lot of modern commercial batteries.
So making the rock half of a battery. Actually, more than half. The nodules also contain significant amounts of iron oxide. Now, in a standard battery, you might use zinc or graphite for the negative terminal, but in these nodules, the iron oxide acts as the negative terminal.
Oh, wow.
And the surrounding medium, the seawater itself, is perfectly salty. It's full of dissolved ions like sodium and chloride, making it an incredibly efficient electrolyte.
That is crazy.
So you have a positive terminal, a negative terminal, and an electrolyte. When Dr. Geiger and Sweetman actually attached electrodes to the surface of one of these nodules in the lab, it produced a measurable electrical current.
A literal underwater rock producing voltage.
Yeah.
And the measurements showed a single nodule producing 0.95 volts of electricity. But here's where it gets really interesting, because there's a significant math problem with that number.
There is a big math problem.
Right. To split water H2O into hydrogen gas and oxygen gas through the process of electrolysis, you need a minimum electrical charge of 1.23 volts. But the voltmeter only showed 0.95 volts. So the battery shouldn't be strong enough to split the water.
Right, it's a critical discrepancy. But the researchers proposed this fascinating cluster theory to explain it. Yes, a single nodule maxes out at 0.95 volts. But on the deep sea floor, these aren't just isolated stones sitting miles apart.
They're everywhere.
Yeah, the CCZ has approximately 21 billion tons of them, spread over 9 million square kilometers. They are densely packed, often resting right up against one another.
Like a giant rock carpet.
Exactly. And when you have millions of these nodules grouped together, they act like batteries connected in a series. If just two of these 0.95 volt nodules are touching, they can generate a combined 1.9 volts.
And 1.9 volts easily clears the 1.23 volt threshold required for electrolysis.
Easily. So the entire ocean floor in that area is essentially a massive interconnected carpet of underwater batteries. They are quietly sending electrical currents through the seawater, splitting the H2O molecules and bubbling up dark oxygen.
The scale of that is just difficult to comprehend. But shifting from the chemistry to the biology, the life surrounding these natural batteries is just as complex. The CCZ is home to something like 5,000 to 6,000 known species, and an estimated 88 to 92% of the life down there is completely undescribed by science.
We don't even have names for most of them.
We don't, and they appear to be heavily dependent on this steady stream of abiotic oxygen.
And if we connect this to the bigger picture, this forces a profound reevaluation of the history of life on Earth. To understand why, we have to look back at the Great Oxidation Event.
Which was, what, billions of years ago?
Yeah, 4.5 billion years ago, Earth formed. But up until about 2.4 billion years ago, the oxygen level in our atmosphere was a mere 0.01%. The planet was populated almost entirely by anaerobic organisms, life forms that didn't need oxygen.
In fact, oxygen was highly toxic to them.
Extremely toxic. But then cyanobacteria in the ancient oceans achieved a genetic mutation. They began to photosynthesize, using sunlight and water to produce energy, and they exhaled oxygen as a waste product.
And because oxygen was toxic to the dominant life forms of that era, this sudden influx of gas triggered one of the most severe mass extinctions in our planet's history.
Exactly. But it also permanently altered the atmosphere, paving the way for oxygen-breathing life, our microscopic ancestors, to evolve and thrive. It gave us the 21% oxygen atmosphere we rely on today.
And the standard narrative has always been, sunlight makes oxygen, and oxygen makes complex life possible.
Always.
But Dark oxygen proves that narrative is missing a massive chapter. Like, life doesn't always need the sun to spark an oxygen-rich environment. The deep sea is harboring ecosystems that are entirely independent of surface photosynthesis.
And the sheer diversity of these localized ecosystems is astounding. Assuming the whole ocean floor is just this barren, uniform desert is a fundamental mistake.
Oh, totally. It's like assuming the entire surface of the planet looks exactly like Mumbai or something.
Yeah.
Just as the surface has rainforest and tundras and savannas, the deep sea has highly localized, highly specialized life in individual trenches and zones.
The microecosystems are incredibly complex, and they often rely on highly specific, temporary energy sources.
The whale fall phenomenon is a perfect example of this. When a 150-ton blue whale dies and sinks to the ocean floor, it doesn't just rot away in a matter of weeks. It becomes an oasis that feeds an entire localized deep-sea ecosystem for up to 50 years.
Half a century. It's
Yeah.
amazing.
First, you get the mobile scavengers like sleeper sharks and hagfish tearing at the soft tissue. Then smaller scavengers like specialized crustaceans and mollusks move in. But the most complex phase happens at the very end, the sulfophilic stage.
Right, that's where the chemical-eating bacteria take over.
Exactly. After the meat is completely gone, for decades, these specialized bacteria feed on the massive amounts of lipids and fats trapped deep inside the whale's bones. As they break down the fats, they produce heavy amounts of hydrogen sulfide gas.
Which is highly toxic to us.
Highly toxic to humans, but it's an absolute feast for deep sea microbes. Those microbes form these thick mats over the bones, which are then eaten by specialized tube worms, which attract squids, which attract fish. One single whale sustains half a century of life.
It gets even stranger when you look at the unique geology down there, specifically the toxic brine pools.
Oh, these are wild. These are literally underwater lakes sitting underneath the ocean.
Yeah, they form when ancient salt deposits beneath the seafloor dissolve, creating pools of water that are 5 to 6 times saltier than the surrounding seawater. And because this brine is so incredibly dense, it doesn't mix with the ocean. It just settles into depressions on the seafloor, creating a distinct surface, complete with shoreline ripples.
Underwater shoreline ripples.
Exactly. And these pools are completely devoid of oxygen and filled with methane and hydrogen sulfide. They're instantly lethal to most marine animals that accidentally swim into them.
But they still sustain life somehow.
They do. They sustain unique, specialized food chains. Methane-eating bacteria line the shores of the pool, specialized mussels circle the pools to filter feed on the bacteria, blind crabs navigate the edge to eat the mussels, and deep-sea predators patrol the perimeter.
It is basically an alien world functioning right here on our own planet. But, it is a remarkably fragile one.
That fragility is a central concern. In late 1980s, test mining operations were conducted in the CCZ to see how feasible it was to extract these polymetallic nodules. They ran a specialized dredge across the seafloor to scoop up the rocks.
And what happened?
Well, that brief localized test devastated 70 to 80% of the macrofauna in that specific spot. And now, over 45 years later, researchers have returned to those exact plow tracks, and the ecosystem still has not recovered. The scars are completely unchanged.
Which brings us to the trillion-dollar conflict at the center of this whole discovery. Because the CCZ isn't just a scientific wonderland. It is an unparalleled geological goldmine. There is an estimated $16 to $17 trillion worth of metals sitting on the seafloor in the form of these battery rocks.
It's a staggering amount of wealth.
And it's not just any metals, right? It's high-grade manganese, nickel, cobalt, and copper. These are the exact critical components the global economy desperately needs for clean energy infrastructure, specifically for electric vehicle batteries.
So you have this intense, immediate collision of interests. On one side, you have the preservation of an ancient, largely unknown ecosystem that is actively producing its own oxygen and supporting uncatalogued life.
Right.
But on the other side, you have a massive mining industry promising to provide the exact raw materials required to transition humanity away from fossil fuels and combat climate change.
So what does this all mean? We are staring down an impossible choice here. We have to weigh a massive discovery that rewrites biological history against an industry that is arguing they can literally save the surface world by sacrificing the deep ocean.
It's a debate that is actively tearing the scientific and corporate communities apart. And looking objectively at the arguments from both sides, it's a highly complex issue. On the mining side, a corporation called the Metals Company, or TMC, has a massive stake in the CCZ. Interestingly, TMC actually spent 12 years and $75 million helping to fund Andrew Sweetman's initial environmental research in the area.
Wow. I imagine if I'm a mining company funding research for over a decade, and that research suddenly produces a foundational argument against my entire business model, I'm going to look for every single methodological flaw I can find.
And that is exactly what happened. When the dark oxygen findings were published, TMC pushed back aggressively. They, alongside independent researchers like marine biogeochemist Bo Barker-Jurgensen from Aarhus University, argue that Sweetman's study has severe methodological gaps.
Like what? What are they pointing out?
Well, for one, Jurgensen pointed out that the controlled lab experiments did not replicate the immense hydrostatic pressure of the deep sea, which is roughly 400 times greater than at the surface.
So they're arguing that the battery effect might behave entirely differently under 5,000 meters of crushing pressure compared to, like, a surface-level lab jar.
Precisely. Second, critics argue that the cluster theory, assuming the voltage jumps from 0.95 volts to the required 1.23 volts, just because the rocks are grouped together, is highly speculative. There's no proven mechanism showing how the electrical current flows between the nodules in open seawater.
Ah, okay.
And crucially, if electrolysis is actively splitting H2O into oxygen-nitrogen gas, where's all the hydrogen?
That's a good question.
The critics claim hydrogen gas levels were not accurately measured or accounted for in the study.
I mean, those are robust scientific critiques. So how does Sweetman's team defend the findings against all that?
Well, Sweetman's team counters that the pressure difference is irrelevant to the fundamental chemical end result of the battery effect. They argue the voltage generation remains consistent regardless of pressure.
Okay.
They also point out that their research wasn't just casually released. It underwent rigorous peer review and was published in Nature Geoscience, which is one of the most prestigious and tightly vetted scientific journals in the world.
Not exactly a fringe blog.
Exactly.
Yeah.
And regarding TMC's criticisms, they highlight the obvious massive conflict of interest. They essentially compare TMC's desire to evaluate the environmental risks of their own mining operations to a cat guarding milk.
Right. And this raises an important question because this debate has rapidly escalated way beyond academic journals. Based on the sheer uncertainty and the potential planetary risks highlighted by the dark oxygen discovery, 33 countries and the International Union for Conservation of Nature, the IUCN, have thrown their official support behind a temporary moratorium.
A precautionary pause on all deep-sea mining.
Exactly. They are arguing that we simply cannot authorize the bulldozing of the seafloor until we understand the basic mechanics of the ecosystem we are destroying.
It's a plea for time, really, to let the science catch up to the commercial technology.
There is a strange, tragic irony in this whole situation, though. We have international coalitions and high-stakes debates focused on preventing potential future damage from deep-sea mining. But simultaneously, humanity is already suffocating these exact pristine environments with plastic pollution every single day.
The scale of the current plastic pollution crisis is almost incomprehensible, and it deeply impacts these same deep-sea ecosystems.
The numbers are staggering. Take the Great Pacific Garbage Patch, which sits directly above areas like the CCZ. It is currently the size of 2 Pakistans, or roughly 3 times the size of Rajasthan.
That is massive.
It holds an estimated 5.25 trillion individual pieces of plastic, weighing around 269,000 tons. And that is just one of 5 major oceanic garbage patches globally.
Yeah, and a major misconception is that this plastic just floats on the surface like a raft of trash. It doesn't. It sinks. During the 5 Deeps expedition, explorer Victor Vescovo descended to the absolute deepest points of all 5 global oceans. He traveled 11 kilometers down into the Mariana Trench, a depth where the pressure could crush a nuclear submarine.
11 kilometers deep.
11 kilometers. And lying there, on the bottom of the world, in one of the most remote and inaccessible places on the planet, he found plastic shopping bags and candy wrappers.
That is heartbreaking.
The plastic is everywhere. And as it sits in the ocean, subjected to UV light and wave action, it doesn't decompose into organic matter. It just degrades into smaller and smaller fragmented pieces, eventually becoming microplastics.
And this is where the environmental crisis crosses directly into human physiology. Because we aren't just polluting the deep sea, we are polluting the food chain, which means we are polluting ourselves.
Exactly.
Recent studies found microplastics in 71% of seabirds. But more alarmingly for us, researchers analyzing fish markets found that 99% of the fish consumed by Americans contain microplastics. In some localized studies, researchers found microplastics in 100% of their seafood samples. The average human is unknowingly consuming between 78,000 and 211,000 microplastic particles every single year.
And the physiological impact of internalizing that much synthetic material is becoming a huge medical focus. A recent research study examined 51 human brain samples to measure microplastic accumulation.
But wait, how does it even get into the brain? The human body has the blood-brain barrier, which is this incredibly strict biological filter designed to block toxins and pathogens from entering the central nervous system.
Well, that is what makes microplastics, and specifically nanoplastics, so insidious. As the plastic fragments get smaller, they become small enough to slip past our cellular defenses. They enter the bloodstream through the digestive tract or the lungs, and because they are on a nanoscale, they can literally cross the blood-brain barrier and lodge directly into the tissue.
Yeah.
In that study, every single one of the 51 brain samples contained microplastics. In some cases, up to 5% of the brain's mass was pure plastic.
That is 6 to 7 grams of plastic. That is roughly the weight of a physical credit card, dispersed and sitting permanently inside a human brain. We are now finding microplastics in the placentas of newborn babies. And in regions where environmental regulations on air and water filtration are less strictly enforced, those exposure numbers could be significantly higher. I mean, regulations are moving at a turtle's pace while human consumption gallops at a horse's pace.
We are rapidly altering environments, both internal and external, before we even understand them. But, regarding the deep sea, the scientific community isn't waiting around. The research into dark oxygen is actively accelerating to find concrete answers.
Right. Armed with a £2 million grant from the Nippon Foundation, Sweetman's team has committed to 3 more years of intensive research running through 2028. And specifically, this year in 2026, they are taking the experiments to the absolute extreme. They are sending their benthic landers and sensor equipment 11,000 meters down into oceanic trenches.
Which is more than double the depth of the initial CCZ discovery. And they have 4 highly targeted goals for this expedition.
What are they?
First, they need to reproduce the original dark oxygen discovery at these extreme new depths. They want to see if the battery effect is consistent across entirely different underwater geographies. Second, they are addressing the mining critics directly by deploying newly designed sensors to carefully and accurately measure the exact levels of hydrogen gas being produced.
To answer that critique.
Exactly. Third, they want to observe if this newly produced hydrogen and oxygen are acting as a direct food and energy source for specialized deepwater creatures.
Yeah.
And fourth, they are deploying advanced biological sterilization techniques to double-check the microbe question. They need to verify completely if unidentified microorganisms play any hidden symbiotic role, or if this phenomenon is 100% abiotic chemistry.
And if they prove this, if dark oxygen is definitively proven to be a purely abiotic process, a major consistent source of life-sustaining gas that does not require a star, does not require a surface, and does not require photosynthesis, it completely rewrites the rulebook for astrobiology.
It entirely shifts the parameters of where we look for extraterrestrial life. Historically, when astronomers use telescopes like Kepler or James Webb to search for habitable exoplanets, we strictly target the Goldilocks zones.
Habitable zones.
Right. We look for planets that sit at the perfect ideal distance from their host star. Not too hot that the water boils away, and not too cold that it freezes solid. We assume liquid surface oceans and sunlight are mandatory for complex life.
Because the assumption has always been that without a star, you couldn't have oxygen. And without oxygen, complex multicellular life couldn't evolve.
Exactly. But if you break life down to its absolute bare essentials, what does it actually need? It needs liquid water, it needs an energy source, and it needs complex chemistry. We already know liquid water exists deep beneath the miles-thick frozen ice shells of moons in our own solar system, like Jupiter's moon Europa and Saturn's moon Enceladus.
Right, those subsurface oceans.
Yeah. And we know energy can be produced in pitch-black environments by extreme heat from underwater hydrothermal vents. And now, dark oxygen provides the final piece of the puzzle, the chemistry. It proves that biological building blocks and life-sustaining gases can be generated in complete darkness, miles below the surface, driven by nothing but the electrical charge of rocks and salt water.
So we might be looking in the wrong places. We don't necessarily need a sun to spark life.
We might not need a star at all. The deep, high-pressure frozen oceans of distant planets and moons could be teeming with complex chemistry, energy, and potentially life.
Which leaves you with this lingering, almost haunting thought to mull over. If biological evolution can be fueled in the pitch-black, crushing depths of our own ocean by nothing but electrically charged stones, could there be highly advanced, intelligent ecosystems trapped entirely beneath the ice of rogue planets?
One's just floating out there.
Yeah. Billions of planets that have been violently ejected from their solar systems, drifting completely alone through the freezing, empty darkness of deep space, inhabited by entire ecosystems of creatures that live, thrive, and die, completely unaware that stars even exist.
It's a profound paradigm-shifting thought. And to think, this entirely